Step one, we need to know how a galvanometer works. I have the red and the black lead here and our little 1.5 volt battery. A galvanometer reads such small current, times 10 to the minus 6 amps, that I put a resistor in there so it doesn't go off scale and possibly damage the ammeter. So I'm going to put this to where the positive current flow is going into the positive side of the ammeter. And watch what happens. It reads positive. If I reverse it and I put the positive going into the negative side, it reads negative. So this will read positive if current is going in here and negative if current is going in there. I've now brought out my strongest magnet that I have. Funny part is I bought this in France. It cost me like $70 just to ship it here. And we're going to use this to see what happens when we put just a single wire through a magnetic field. Now the first thing obviously we need to do is we need to figure out what the direction of the magnetic field is. So I have a compass here and let's see what it says. Well, the north pole is facing there, the south pole is facing here. So this is the north and that's the south. Let me check with a known magnet. Here's a north pole of a known magnet and it is strongly attracted to that side. I'm not going to let it go, it'll be hard to pull off. So north to south. Let's go ahead and write that on some paper, sticky notes, so we can remember that. The magnetic field is facing that direction from north to south. That's the direction of the magnetic field. So now let's go ahead and put a wire through there and see what happens. Okay, it's connected to the ammeter, which we already know how an ammeter works. If I take this, here we go. I'm going to push this straight down. Once again, from down, you should hopefully see that it's reading positive. Okay, now how does that work? Well, magnetic field is moving this direction. I am pushing the charges in the wire down. So it's creating a force along the wire that direction, the direction of my palm, which goes into the positive side of the galvanometer and moves it in the positive direction. Once again. Now what about if I pull it up? The magnetic field is still going that direction. I'm moving the charges in the wire upwards. The force is going this direction, which following it will go into the black lead and read negative. Positive, negative. Once again, positive, negative. Now to visualize this, I've created this device here where it's just a bucket with a bunch of, so I notice it says magnetic field demonstrator. It has water, and the water is to help you visualize the magnetic field. The magnetic field is going down. Let me get this where you can see a little bit better. There. Now let's pretend that this right here is the wire that we just put through the magnetic field. If I take the wire and I move it this direction, the magnetic field is going down, the wire is going this direction, the magnetic field will go that direction, the magnetic force will be that direction in the wire. Again, magnetic field, charges in the wire moving this direction, the force in the wire, which will create a current, will go that direction. Likewise, magnetic field down, the wire is going that direction, the force would be towards me. That's exactly what happened in the thing that I showed you in the front. I have a different magnet now hooked up here. This one, this is the north and the south. To prove that, we'll also use a compass here real quickly and point that positive points towards south. North towards south. So the magnetic field is pointing that direction. I now have the galvanometer hooked up to a large coil of wires. Let's see what happens as I move it in and out of the magnetic field. A lot of current, a lot of current. So moving it in and out produces a lot of current. Watch what happens when I move this direction. Very little magnetic, right here. Notice there's very little, see how the bottom wires are actually moving parallel and they're not getting a lot of magnetic field, or not getting a lot of current. If I go like this though, I get a lot of current. Okay, so moving parallel to the magnetic field. The problem is I get really, so here, let's see if I can move just like this. Notice I'm not getting much, a little bit, but that gets me a lot. Okay, another thing. Let's go back and prove that with the water. It's raining once again. So now in this case, I have my loop, and when I move it in, there's a magnetic field, there's an increasing, when I move it in, I get electric current. When I move it out, I get electric current. When I move this way, I don't get a lot of electric current. We can explain that again with what we did here. So if I move it this direction, again, or sorry, we can move this way. If I move it this way, remember that we get the magnetic field, charges, the forces that direction. So on this side of the loop, as I move it into the magnetic field, it feels a force causing the current to go this direction. If I pull it out, magnetic field, wire, the force would be this direction. But if I move this direction, do you see how, like the wire is moving parallel to the magnetic field, and you're not going to get any current in the wire. Now, before we do the next thing with the magnets, I want to prove the concept of flux, or I want to talk about the concept flux. Flux is field times area. See how right now I get a lot of water going through that circular area? That would be a lot of magnetic flux. Flux, however much that is, the field strength, which would be in Teslas, and the area, which would be in meters squared, would give you the flux. Right now, there's no water going through the area, so there would be zero flux. Increasing flux, decreasing flux, zero flux. Let's go show that with a magnet. So the idea of flux. Right now, the magnetic field is going that direction through that circular area. So this would be maximum flux. This right now would be minimum flux. The magnetic field is not passing through the area, it's passing by it. Now I'm going to hook this up to make this easier on me. Hold on a second. Now you can see that I've got it hooked up to where I can spin the magnetic field. So right now, don't concentrate on that. Let's just worry about over here. So notice right now there's no flux going through the coil. Now there's maximum flux going through the coil. Minimum flux. Move this over a little bit. Minimum flux, maximum flux. Minimum flux, I don't have it in the center, that's why it's driving me crazy. Maximum flux, minimum flux. Now let's look over here and see in which case we get the most induced current in the coil. So right now, notice we're getting a lot of induced coil and a lot of induced current, and we have a minimum of flux. Right now, we have a maximum flux, but we have very little induced current. Now, ways of thinking about this. You see here that so let's just spin it. The other thing you notice goes negative, positive, negative, positive. And notice the maximum is right now when that's breaking the magnetic field lines. Another way to think about this is right now it's moving the coil, think about it as up and down, is going, the magnetic field is going this direction, either, so I guess that's north, going that way. It's moving perpendicular to the magnetic field lines right now. So that's why it's going to get a lot of induced current, because there's a lot of right-hand rule force there, the Lorentz force. Right now, you see how it's moving this direction relative to the magnetic field? That's basically parallel. I can even move it right in the magnetic field, and you're still not getting very much because it's basically moving parallel to the field. All right? So, once again, maximum flux when it's moving perpendicular to the field, minimum flux when it's moving parallel to the field. Let me go show you this with the water. Now, let's show why it's stronger when it's parallel, or stronger when it's got less flux. So, once again, with our rod here, notice that the rod is going parallel to the field. By the right-hand rule, there can be no force in the wire and no induced current. If it's going this way, it's breaking the field lines, it's moving perpendicular, okay? Likewise, here, notice this, pretend it's this wire going like this. Even though there's a lot of flux in that area, the sides of it are moving parallel to the water, parallel to the magnetic field, and there would be no induced current. Here, it's moving perpendicular to the magnetic field. There would be current in that loop, okay? Now, why does it change direction? I want you to notice, see this little opening right here? We're gonna use that for our, to keep track of which side is which. Just to make this easy, when the wire is going this direction, magnetic field, current is that direction, right to my right. Make sure you can see. Okay, so magnetic field, wire, the current, my hand is pointing inwards. So that would be the direction of the current in the wire. So if it's moving this direction, the current is that direction. If it's moving to my right, the current is away from me. So now, see how this wire by itself Notice the opening here. The wire is going that direction, so its current will be going this direction all the way around, away from the opening. Right now, there would be nothing. There would be no induced current. This wire is again moving that direction, so the current's going this way towards that opening. So right now, the current is going this direction in the loop. Now there's nothing. Remember, it was going this way. Now it is flipped. It is now going this direction in the loop. Then there's nothing. So the wire, so let's just look at this side right here. Going that direction, going this direction. Going that direction, nothing. Going that, it keeps flipping directions. Okay, and that's why you get a change of current in the loop. Now the next thing to do with flux, we need to do Lenz's law real quickly. So let's go do that.